In this section, we're going to study free fall. So that is the study of objects that are moving vertically, and so they are falling with the acceleration of gravity. So one experiment that has been done for ages, it was even done in the moon, is if you drop two objects with different masses, they'll fall with the same acceleration. So the acceleration is the same, and on Earth it is just g, which has minus 9.8 meters per second squared. We'll talk about this minus in a little bit, but here in this slide we have a few ways to visualize the free fall. We have a motion diagram here. Here is the motion diagram, and then you can see the acceleration always points downwards towards the ground, and here we have the velocity increasing at the same in the same direction as the acceleration. So this object is speeding up. This is equivalent to dropping an object. If we plot the velocity versus time graph, we have time here in the horizontal axis in seconds, velocity in meters per second, and then what we see is that the velocity versus time graph is a straight line. Is this a straight line here? The slope, the rise over the run of this thing would give you 9.8, and it's a negative slope. It is a negative slope, so that is the acceleration of gravity. And if we throw an object upwards, if we throw it up, then what is going to happen is that the acceleration is always going to point down, but here the thing is going to slow down until it reaches a maximum. So the acceleration of gravity, which we denote by g, and this is the magnitude of the acceleration, and it has this value here, 9.8 meters per second squared. So that means if you drop an object after the first minute, the speed is 9.8 meters per second. After the second minute, the speed is 19.6 meters per second, and so on. That is what this means. That is the standard value of acceleration that we're going to use for most problems. Here in the slippery rock is a little bit different from that, and we are going to measure that value with some accuracy in the lab next week. So there are some key points here. G is a symbol that we are going to use to denote the acceleration of gravity, the magnitude, and it's a positive. This is a number, it's 9.8. The value of the acceleration of gravity, the sign, the direction of the acceleration of gravity is going to depend on how you choose your coordinate system. If you choose a coordinate system that points up, then the acceleration of gravity is the direction of the acceleration of gravity is going to be negative. If you choose a system that points down, then it's going to be positive. So we can use the kinematic equations for constant acceleration to solve all problems with free fall. And so those are things to remember here. So here's a quick question. You throw a ball on the earth, you throw a ball up, so the ball is going to do something like this. It's going to go up and down, so it goes up and then it comes down and it reaches a maximum point, right? At this point here, at that maximum point, what is the instantaneous acceleration of the object? Take a minute to answer this question. So, and the maximum acceleration is going to be, well, is g, right? The acceleration is g all the time. It doesn't change. So the acceleration at this point is g. It points down. So it's a negative acceleration because we've chosen the coordinate system pointing up. Here we have another problem. We throw an arrow and the arrow goes up and down. So at which point in the trajectory, A, B, C, D, or E, at which point is the acceleration the greatest? Take a minute to answer this question. And then again, the acceleration doesn't change, right? Acceleration is going to be the same because it's gravity, so it's g all the time. So the acceleration here is the same as here, it's the same as here, and as here, and as here. So it's the same all the time. Here we have another problem. So we have this arrow going up and down, and there are 5 choices of velocity versus time graph. Which one is the right one? Let's take a minute to answer this question. And if you chose this one, that is the right one. So here we have that the velocity is decreasing as you go here. It reaches 0 here, and it increases, and the speed increases, and the velocity becomes more negative. So velocity decreases, reaches 0, and then it starts becoming negative, and the speed increases in that part. The slope of the velocity versus time graph, which is the rise over the run, that slope is going to be negative and is minus g. Okay, let's look at a problem here, a typical problem that you might get in an exam. So you have a heavy rock that is dropped from rest from the top of a hill, and it falls 100 meters before hitting the ground. How long does the rock take to fall to the ground, and what is the velocity when it hits? So, and again, when solving these problems, it is always useful to draw a picture. So here we have a motion diagram picture for this. So we can see that the acceleration is g, and it points down, and then you drop the ball, and the velocity is increasing, and you start here. So this is your initial time, this is your final time. So if we draw a coordinate system, we are going to have the coordinate here, and we are going to choose a coordinate system where everything that goes up is positive. So in this coordinate system, the acceleration is minus g. And now we can go ahead and start naming things. So we have initial and final here. So y initial, we can always choose a coordinate system, the origin, to be anywhere. So we're going to have our 0 here. So this is going to be 100. So our y initial is 100. Our y final is going to be 0. Our v initial is 0 because you're dropping it from rest. Our t initial, we're going to set our stopwatch to be 0. The acceleration is minus 9.8, and we need to find the time and the final velocity. So to do this, well, let's just look at how to do this. So we have our 3 equations. So the first one that we're going to use is y final is equal to y initial plus initial velocity times delta t plus 1/2 a delta t squared, and this a is minus g here. So this equation, then I write it using g, so I have y initial minus 1/2 j delta t squared. This guy is 0 because it's the initial velocity, so this is all I'm left with, this here. And I can rewrite this as in this here, since tf minus ti, which is delta t, that is equal to tf, because we chose ti, this to be 0, right? So that is our equation now. And from here, I know yf, right? That is y final, which is 0. I know this is 100. This is 100. So then I can solve for this, and I get that that's 4.52 seconds. That's the time it takes to fall 100 meters. So now to solve for the velocity, we are going to use the equation Vf is equal to Vi, and this is square, plus 2 times A delta y. And A here, of course, is going to become G, and then I have a minus here because of the acceleration. So that is our equation, so I can put it right here. Well, actually, yeah, I can use this, or I can use this other equation, which is the one using in the slide, sorry. So Vf is equal to Vi plus A delta t, right? I know the time now that I found here. So then A is what? A is minus g. And now I can plug everything here. I can plug this, I know this, and I know this guy and this guy, so I can solve, and I find that that is 44 minus 44.4 meters per second, and it's a negative velocity.